Hey everyone, welcome to this explainer. Today we're zeroing in on a very specific goal. We are going to completely master the formation of Troostite. Now, if you're gearing up for those metallurgy certification exams, whether you're aiming for a technician, industrial engineer, or master craftsman, you know that understanding these tempering stages is absolutely non-negotiable. But listen, we aren't just going to sit here and memorize dry facts today. No way. We're going to build a clear, logical mental model of exactly what's happening inside that metal on a microscopic level. By the end of this, Troostite isn't just going to be some fancy vocabulary word to you. It's going to be a dynamic process you can easily visualize and remember. To get us there, we've got a quick roadmap. We'll start with a recap of stages 1 and 2, then turn up the heat for stage 3, define exactly what Troostite is, compare its microstructure, and finally, look at some real-world applications. All right, let's jump right into section 1. Stages 1 and 2 recap, setting the baseline. Because context is everything in metallurgy, right? Before we can really appreciate the third stage, we have to know where we're starting from. So, everything kicks off with stage 1. This is where we establish our Martensite base. It's super hard, but as you already know, it's highly brittle. From there, we move up the temperature scale into stage 2, which sits roughly between 200 and 250 degrees Celsius. And that sets us up perfectly for our main event today, stage 3, where we push that heat from 250 all the way up to 400 degrees Celsius. Now, just a quick side note on stage 2 before we move on. The primary focus here is the transformation of any retained austenite into bainite. But, if your specific cooling process didn't actually leave behind any retained austenite, which honestly happens a lot depending on your carbon content and how you quenched it, this stage kind of just doesn't do much. So for our purposes today, unless we explicitly know we're dealing with retained austenite, we can basically just bypass stage 2 in our heads and keep our focus tightly locked on going straight from stage 1 into stage 3. Which brings us to section 2, the heat of stage 3, dramatic chemical shifts. This is where things get really interesting. Seriously, lock this number into your brain for your exams. 250 to 400 degrees Celsius. When we blast our Martensite base with a specific band of heat, we're feeding it the exact thermal energy it needs to force a massive, and I mean massive, structural change. So what actually happens at that temperature? Well, we see a staggering 90% of the remaining carbon just abruptly release from the Martensite structure. Remember, back in stage 1, only about 10% of the carbon precipitated out. But here, the heat literally forces that remaining 90% to completely rush out of its trapped state. It's this rapid, microscopic evacuation of carbon, and it fundamentally changes the entire nature of the steel. And that mass evacuation creates something entirely new. Let's look at section 3, defining Troostite, the resulting microstructure. Enter Troostite. This is the star of the show, the distinct microstructure that forms right here in the third stage of tempering. And hey, here's a fun little nugget to help you remember it for your test. It's actually named after the pioneering French scientist, Louis Joseph Troost. I always find that putting a human face or name to these crazy technical terms makes them way easier to remember when you're sitting there staring at an exam paper. But let's get into the weeds. What exactly is it chemically? Well, as all that carbon rushes out, it has to go somewhere, right? It precipitates and settles. So what you're left with is a ferrite matrix. Think of that as your soft base material. But dispersed all throughout that base is what we call fine granular cementite, or Fe3C. Basically, the carbon recombined with the iron to form these incredibly tiny, fine granules of cementite, and they're just embedded right into that softer ferrite background. Let's move on to section 4, microstructure comparison, shapes of the metal. To truly wrap our heads around Troostite, I want you to think about this for a second. We know the ingredients now, right? Ferrite and fine granular cementite. But how does that actually look when you put it under a microscope? How is Troostite fundamentally different from stuff we already know, like Pearlite or our starting Martensite? Comparing them side by side really makes it click. Look at Pearlite. It forms in a lamellar shape, so think distinct, alternating layers. Then you've got Martensite, which is super needle-like, very sharp and jagged. But Troostite, it's totally different. It's characterized by its fine, granular shape. Recognizing this visual contrast, layers versus needles versus tiny little granules, is an absolute must-know for your exams. It's basically the visual fingerprint of the metal. All right, let's bring it all together in section 5, real-world application, from micro to macro. All these microscopic granules are super fascinating, but how does this actually translate into the real world of engineering? Well,
When you compare our starting material to our end product, the difference in physical properties is literally night and day. Untempered martensite is intensely hard, for sure, but it's way too brittle. If you hit it, it shatters. It has zero give. Troostite, on the other hand, gives us this magic combination. Because you have that softer ferrite matrix holding those hard little cementite granules, Troostite stays really hard, but it adds an incredible amount of toughness and durability. It's not just going to shatter the second it takes an impact.
And that brings us to the ultimate payoff. Because it strikes this perfect Goldilocks balance of hardness and toughness, Troostite is the absolute ideal microstructure for tools that have to take a serious beating. Think about concrete cutter blades. If you made a cutter blade out of pure martensite, the literal second it hit solid concrete, it would just snap and shatter into a million pieces. But by tempering it up to stage 3 and creating Troostite, that same blade stays hard enough to slice right through solid rock, but it's tough enough to absorb all those violent, intense vibrations without breaking. Pretty cool, right? So we've successfully navigated that 250 to 400 degree range, and we've unlocked the tough, durable secrets of Troostite. But it leaves us with a pretty fascinating question. If stopping at 400 degrees gives us this perfect granular balance for something as intense as cutter blades, what kind of crazy structural transformations are waiting for us when we push the heat even higher? What happens when we cross the threshold into tempering stage 4? Well, that's a journey into sorbite, and it's exactly where your metallurgical studies will take you next. Keep this mental model sharp, and you are going to absolutely crush those exams. Thanks for joining me on this explainer, and I'll catch you next time.